Okay. So deep learning is having real world success on structured data like images, text, and audio. And this has generated a lot of interest in applying deep learning to 3D computer graphics. In computer graphics, we really love meshes. They're fast to render, they're intuitively editable. We can efficiently add textures, we can deform them, we can achieve a high level of detail, they're adaptive, and so on. Applying deep learning on meshes can open the doors for a lot of amazing applications in computer graphics, like generative shape modeling and synthesis, shape editing and deformations, surface mesh reconstruction, and different shape analysis tasks like symmetry detection, feature learning, shape matching, segmentation, just to name a few. But extending deep learning that works on structured data like images and text to meshes is not so straightforward. We can roughly categorize these difficulties into two key challenges. The first is the mesh representation itself, and the second is the mesh data. So the mesh representation is irregular, it lacks structure, and this is unlike 2D images or 1D signals, which are defined over evenly spaced integer intervals. Meshes are defined by a list of vertices, which are glued together by triangle faces. And since each vertex can have an arbitrary number of vertices in its one ring, we can't trivially use standard neural network operators that assume fixed size pixel neighborhoods, for example. And there's no order in the list of mesh vertices and faces. We can change this order and still have the same exact underlying mesh object. But standard neural network operators do rely and utilize on some notion of north, south, east, west ordering of pixels on an image grid. And the mesh triangulations themselves are highly inconsistent. The same exact object can be represented using many different underlying meshings, which is unlike images that always have a structured grid topology. And while images exhibit a strong bias towards an upright direction, meshes can be given in any orientation. Data is key to deep neural networks, but in 3D we have a data problem. There is a lot of 3D mesh data out there in the wild, created by different people that we've acquired over the years, but this high visual quality doesn't imply compatibility for geometric computation. A lot of this data in the wild is not manifold, not watertight, contains self-intersections, has polygon faces with incorrect normal orientations, among other problems. And our geometry processing algorithms may not always be able to effectively handle these cases, and so this will ultimately restrict the amount of data that we can train on. And if we need to create more 3D data by hand, it's still difficult and mentally taxing even for the most seasoned experts, since modeling software is still very manual, tedious, and unintuitive. Oops. To top it all off, the third dimension in our geometric data compared to the 1 or 2D counterparts increases the space of possible scenarios so much it requires an exponentially larger amount of data, which is basically the curse of dimensionality. In this course, we're going to discuss how to effectively use deep learning on mesh data in spite of these challenges. First, we'll go through some fundamental concepts of neural networks and derive intuition for how to build them on the irregular mesh representation. And then we'll go through a few applications of these deep learning architectures on meshes, which avoid some of these 3D data issues by training on a single example. Before diving into meshes, though, I want to just briefly mention that there are alternative ways to represent 3D shapes. Each representation has its own pros and cons, especially within the context of deep learning. 3D voxel grids define occupancy at regularly spaced intervals, and they're structured like 2D images, and this makes applying standard deep learning operators straightforward. But they're really inefficient and low resolution representation, and this exponentially large memory footprint does pose a very big challenge for deep learning currently. Implicits represent the surface as a function, which gives assigned distance for every point in space. A big advantage is the ability to handle changes in genus well, and this is part of the reason why implicits are becoming an increasingly popular approach for synthesis tasks in deep learning. But they're not directly suitable for deep learning analysis tasks. And they're also inefficient and struggle at sharp features. The point cloud, which is a list of unordered XYZ coordinates in space, is the most popular representation for 3D deep learning today. A big advantage of point clouds is that they're flexible, which enables us to easily train on data sets which we may not be able to train on when using other representations like meshes or implicits. But point clouds struggle to accurately represent sharp features. They lack surface connectivity information and are very inefficient. They're also not intuitively editable, and it's not even easy to render a point cloud. The mesh has all the advantages that I mentioned earlier. It has a high level of detail, it's adaptive, it's efficient, and so on. And today we'll see that we can leverage these advantages within the context of neural networks in spite of these challenges. From a 10,000-foot view, learning on meshes starts with a mesh input, which goes through some black box neural network, which provides some output. This output can be anything like a high dimensional shape descriptor, a probability to collapse an edge, a displacement vector per vertex, a segmentation label per face. These are just a few examples. And the basic unit of any neural network is a neuron. It takes as input X values and applies a weight theta to each of them, sums the results, and then goes through a nonlinear activation function before being output. Let me illustrate this concept with a simple geometric example. If we wanted our neuron to produce the perimeter of a rectangle where the inputs are the length and the width of the rectangle, then if each weight is 2, our nonlinearity is ReLU, our neuron would produce the perimeter for any valid input. And the way that we would train this really simple network is by feeding the network supervised pairs of inputs and outputs. And we'd initialize the weights to some small random value and evaluate the fit of each example and update the weight values in the negative direction of the gradient. A collection of neurons is called an MLP, multi-layer perceptron. But how exactly to connect and combine these neurons in a way that makes sense for our problem is really important. The most vanilla MLP is a fully connected layer. That means that all of the inputs are connected to all of the outputs. And note that this doesn't scale well to very large inputs. Like we can't have too many X's, but we'll see shortly how we can overcome this. Building a deep network for meshes, but also just in general, requires considering what type of inductive bias we want to incorporate into our models. Inductive bias is another way of saying the set of assumptions that we encode in our network, which will make our network better suited for the task. And I want to reiterate this point because it's super important. Inductive bias is the assumptions that we force the network to have, and that's going to make the network perform the task better. And these assumptions are based on our domain-specific knowledge. Oh, no. By incorporating the right inductive bias, we can make progress towards a big goal in machine learning, which is creating a system that is robust to irrelevant variations of the input. And in the case of meshes, this can help us design networks that can handle the problems that we discussed earlier, like handling irregular, unstructured, and unordered mesh vertices and bases. We can build deep networks for meshes for a variety of tasks, and let's roughly categorize them as global and local. In a local task, the network takes a mesh as input and predicts some value on every mesh element. This could be anything from a descriptor per vertex or a probability of whether to flip an edge, or a segmentation label per triangle face. For global tasks, we want to aggregate over all of these local deep features to predict a single output for the entire shape, and this will give us some, for example, probability that the shape belongs to a particular category or a high dimensional signature that tells us its proximity to other shapes. Let's start by looking at a network built for local tasks, like predicting a segmentation label per triangle face. It takes as input a list of faces and predicts a probability vector for every single face, which class it belongs to. So how do we build this network? We should not use a fully connected network because it would connect every single input to every single output, and that would mean that it would be sensitive to the arbitrary ordering of the mesh faces. So given the same exact mesh, there's no consistent canonical ordering for this list. It's unordered. And this is going to result in different outputs if we use a fully connected layer. It also doesn't scale to very large inputs. So as the number of faces will grow, the number of parameters in the network will become intractably large. So a fully connected network will result in a system that is sensitive to this irrelevant variation of the input list ordering for the segmentation task. And we can think about how to build a deep network with the right inductive bias by drawing inspiration from a similar phenomena that happens in images. In images, fully connected networks are also not suitable for predicting a segmentation label per pixel. And the take-home message from the image domain is to use a neural network which shares weights across each pixel and its local neighborhood. Shared weights means we apply a narrow MLP across the entire image, where the same weights are applied in every location. And this is nice because a small shift in the input image will result in the same small shift in the output segmentation labels, and this is called translation equivariance. And another nice thing about this shared weight network is that it will also scale to much larger input image sizes. In images, the most common way to share weights using neural networks is through a convolution operation. Convolution is a square filter of learned parameters that's applied by element-wise multiplying each pixel and the pixel neighbors with the corresponding values in the filter. And these are then summed to get the feature activation for that pixel. And this filter is shared. So it extracts the deep features across all of the pixel neighborhoods. And convolution is a pattern matching operation, right? It looks for interesting local spatial relationships in images, like detecting edges, corners, and textures. Extending this same weight sharing convolution to meshes will result in a similarly powerful inductive bias, which will also share weights across local triangular patches. The idea is to train a shared weights neural network over the entire mesh, which will produce a descriptive signature for every mesh element. But this isn't straightforward like it is on images, because there's not a fixed number of convolutional neighbors, and there's no ordering between them. So some of the first works proposed handling these ambiguities by treating each local vertex neighborhood as a small disk, which can be flattened to the plane. And the general idea is to bypass the irregular structure of the extrinsic vertex neighborhood and instead treat it as an intrinsic problem over a local circular disk. One of the first works to do this discretized this disk into pie slices and then learns a kernel over each of the pie slices. There's been many follow-ups since, and the inductive bias of intrinsic operations on meshes is great for intrinsic things, like being invariant to isometries and different triangulations of the shape. Alternatively, we can have a more extrinsic take on this by directly learning over the mesh structure, which will be especially useful for shapes with sharp edges and can be important for things like learning to displace vertices, editing mesh connectivity, generating new mesh connectivity, and so on. So in this section, we're going to discuss several different ways to apply convolutions directly on the mesh structure and over different mesh elements. Each vertex doesn't have a consistent north, south, east, west between the vertex neighbors in its one ring. But when we think about meshes, we think about this list of vertices and faces, but we do have an edge. In our mesh CNN work, we leverage the fact that mesh edges do have a fixed number of neighbors, since every edge is adjacent to exactly 2 triangles in a manifold watertight mesh. And this will give us a fixed size neighborhood of 4 edges. We utilize these fixed size neighborhoods to learn deep features on each edge and the 4 neighboring edges. Every edge in the mesh is like a pixel in an image. It has an n-dimensional feature vector associated with it. And we learn convolutional filter weights, which are applied on each edge feature vector and the 4 neighboring edge feature vectors. But we still don't have a consistent ordering, right? Because depending on the initial ordering of the edges, we're going to get different configurations, which means we won't be able to consistently match the corresponding kernel values of the convolution and the edge features. In other words, directly convolving kernels against features associated with edges will be sensitive to the edge order. But we do have a face normal. The direction of the face normal defines a consistent ordering within each face. So depending on which face we start with, there's 2 consistent orderings for the 4 neighbors of each edge. This will ultimately result in an ambiguity between the edge features in A and C that are in red and B and D in blue. The solution that we proposed is to apply a simple symmetric function on these ambiguous pairs, and then apply convolution on these symmetric features. And the way that these symmetric features are created is by element-wise adding the features in A and C and taking the absolute value of the difference between A and C. And the same thing goes for B and D. The result is a convolution which is invariant to the initial edge ordering, but can still learn to exploit interesting spatial relationships and find patterns within local neighborhoods like in images. Edges of the mesh are like pixels in an image. They start out as a low dimensional feature vector of RGB values, and that's later abstracted by the network to some high-level semantic features. In the same way, edges start out as a simple 5-dimensional geometric feature vector, the 3 angles in blue and the ratios of the height to the base of each of the triangles. And you can note that these features don't contain the absolute X, Y, Z coordinates explicitly, and that's because they're relative. So that makes them invariant to similarity transformations, rotation, translation, and uniform scale. And that will, when combined with our equivariant convolution, will lead to a system that's invariant to similarity transformations. To recap where we are so far, we built a network by extracting features over each mesh edge and then applying a series of convolutions in sequence, which results in a per edge feature vector, and we can use that to predict a segmentation label per edge or some other local attribute. But convolution might be too local of an operation. For example, we might want to incorporate more context to properly perform the task, because different patches might look very similar even if they're in very different regions. And the size of the input, which is responsible for creating the output feature, is called the receptive field. And as we add more and more convolutions in sequence, we can increase this receptive field. But a more efficient way to increase the size of the receptive field and incorporate more context is through pooling. We again take inspiration from images, which incorporate a downsampling operation to decrease the resolution of the input, which is going to make far away regions closer. Pooling works in images by taking a square window and sliding it across the deep features of the image. And in the case of max pooling, is going to take the maximum value in each window cell. Then we can restore the original image size by unpooling the downsampled deep features back to their original maximum locations. And with meshes, we would ideally like to incorporate a similar pooling operation in order to increase the receptive field, gain more context, and strengthen the learned representation. But unstructured mesh data doesn't downsample in the same way as a structured image. In computer graphics, we have a way to reduce the size of meshes using edge collapse. This removes edges so as to best preserve the original shape. In Mesh CNN, the network learns which edges to collapse, and that's based on the deep edge features instead of geometric ones. And this reduces the size of the deep features, increases the receptive field, and strengthens the learned features. But it also enables us to visualize which part of the shape the network determined should be deleted. Mesh pooling takes the L2 norm of the learned edge feature vector and then deletes the k edges with the smallest norm, where k is some hyperparameter of the mesh pooling layer. And deleting a single edge has two core operations. First, we generate the new mesh pooled features, and that's by aggregating the features of the three edges in each triangle, which are collapsed to a single edge. So P is generated by element-wise averaging the features of A, B, and E. And second, the relevant mesh data structures that contain the adjacency information, they're updated so that when we go to apply the next convolutions, we'll have the correct 4 convolution neighbors for each edge. After pooling reduces the number of edges, we can apply unpooling layers to uncompress the edges back to the same number as before pooling. Unpooling records the mesh topology before mesh pooling and then reinstates the same mesh connectivity. Besides for the connectivity, we generate unpooled features, which are just a weighted average of the pooled features. And both unpooling and pooling in meshes and in images is not a learnable layer, so they're followed by convolutions. A unique property of mesh pooling, which is different from pooling in images, is that it's task-driven, and it enables us to visualize what the network learns. So if we train one mesh CNN network to classify whether the shape has handles, and we train a second network on whether it has a neck, the network will successfully remove the irrelevant parts of the shape and focus on the important ones. And I think this is really cool because it gives an interpretable neural network where we can actually see what the network is learning and whether that's aligning with what we think it should be doing. So now if we put everything together, we stack the mesh convolution, mesh pooling blocks together in sequence. They form our mesh convolutional neural network. The network learns deep features on the mesh edges and exploits this unique property of triangle meshes, which have fixed size 4 edge neighborhoods, which we can use to do classification and segmentation. In the case of segmentation, since the pooling layers reduce the resolution of the input, we can restore the original resolution prior to pooling by adding unpooling layers, and then we can predict a segmentation label for every edge in the input mesh. When building a classification network, we don't actually need to use the unpooling layers. Instead, we can just aggregate all of the deep features over the pooled edges into a single permutation invariant descriptor using global pooling. And that means we apply a max or an average operation across the different feature dimensions of all the edges. And then we can use a few sequential fully connected layers to produce the probabilities for the category of the input mesh. And also here, since the network learns which edges to collapse, we can inspect how these intermediate mesh pooling results look. So here we show an application of mesh CNN to a 30 class classification of shapes, and we compare it against approaches which parameterize meshes to images and use image-based CNNs in addition to more classic 3D shape analysis, handcrafted descriptor approaches. So something interesting that we noticed is that for a particular class, like men, the mesh pooling removed their heads, but for a different class, ants, the network removed their legs. So there's something different and consistent happening across these classes. We also built a special classification dataset to highlight the power of the mesh representation over the more popular point cloud representation in deep learning. So we took icons from 23 different classes and created shallow engravings from each class of icons into a cube, which defines the category it belongs to. And when we represent this shape as a point cloud, it's really difficult to tell which engraving this has. You probably can't tell, but when we represent it as a mesh, you can more clearly see. And so not just qualitatively, but also quantitatively, there's a significant improvement in using mesh CNN over point networks. Another interesting thing is that we can look at these intermediate mesh pooling results. So these are test examples that the network never trained on. And we can see that it's collapsing, deleting background edges, which does encourage us that it's learning the right thing and not just overfitting to noise. These are the results of mesh CNN on a human segmentation benchmark. And we compared against existing techniques that work on point clouds or intrinsic methods. And after mesh CNN, there's been a lot of different follow-ups and improvements and variations to this sort of architecture. One of these works is neural subdivision, which extends the idea of learning on undirected edge neighborhoods, as we did in mesh CNN, to directed edge neighborhoods, which they call the half flat. And this work learns deep features over the directed half edge. Here, convolution is applied on a fixed number of neighbors because there's, again, always 4 edges in a one ring, which means there's always 4 vertices. And this work learns deep features over the 4 vertices for each directed half edge, which are constantly ordered by the face normal. And each new vertex feature is obtained by just averaging over all of the half edges that are pointing out of it. So the initial set of input features is also differential in this work. It's a local coordinate system that starts at the source vertex of each half flap, as well as a differential coordinate for each vertex. And there's an alternative way to do pooling, which is instead of reducing the size of the feature activations, we could just directly coarsen the input, reduce the resolution of the input. So in neural subdivision, the mesh is coarsened by randomly collapsing edges, and then different networks learn over these different mesh scales. And I think it's an orthogonal approach for increasing the receptive field of neural networks. So this is not precisely a convolution operation, but it's similar in spirit. Meshwalker presented the use of recurrent neural networks over random walks to describe the surface geometry and topology. Once a random walk is extracted from a mesh, it defines a sequence that's used to train a recurrent neural network. And in this case, it was a GRU, gated recurrent unit, where deep features are learned over the vertices of each walk. And the idea is that these random walks explore both the local geometry of the surface as well as more global terrain. Starting with a vertex, the next step in the walk is generated by randomly selecting an adjacent vertex until the length of the walk is the number of total vertices in the entire mesh divided by 2.5. The input features of the walk are represented by differential XYZ coordinates from the previous vertex in the walk, and then a GRU network is trained over these ordered walk sequences, which can ultimately be used to predict values per vertex. Triangles also have fixed size neighborhoods like edges, because each triangle is adjacent to exactly 3 faces in a manifold watertight mesh. In this work, we proposed learning deep features over each triangle by learning convolutional kernels, which are applied on each face and the 3 neighboring faces. The input features are defined on a local coordinate system, which is the direction of the half edge and the face normal. And this local basis is used to extract a 4-dimensional feature vector, which is the edge length and the Cartesian coordinates of the opposite vertex to that edge in the relative coordinate system. We removed geometric textures from a textured mesh using a mesh simplification, and then rebuilt back the texture to the original geometry using a fixed loop subdivision connectivity. And we trained a series of progressive generators on each mesh resolution, where the finest resolution contains the largest receptive field with respect to the original mesh. PD mesh net defines convolutions on both the primal and dual graph from an input mesh in order to learn over both the faces and edges of a mesh. So primal graph of a mesh has a node for every face in the original mesh and an edge connecting adjacent faces from the original mesh. And the dual graph has a node for every edge in the original mesh and an edge between adjacent edges from the original mesh. The convolution is then learned in an alternate fashion on the dual and primal graph using a graph attention-based network. And the core idea of graph neural networks is message passing. Basically, aggregate information from incident nodes to each node, so like average over each node neighborhood, and then apply a 1-by-1 convolution on each messaged passed node. PD MeshNet also proposes a task-driven pooling operation for downsampling the number of features in the network by contracting graph edges. So PD MeshNet contracts edges on the primal graph, which corresponds to a face merge on the original mesh. And since their convolution is suitable for a general graph, not just specific to triangle meshes, it doesn't require producing or preserving a valid manifold triangle mesh. In a recent follow-up work, the mesh pooling layer from mesh CNN was further enhanced. So in the original mesh CNN work, each pooling layer collapsed the k edges with the smallest norm, and the mesh data structures were only updated at the end of the mesh pooling layer for efficiency purposes. So for example, the original mesh, if the original mesh CNN collapsed this edge and then this one, in the new version, after the first edge is collapsed, the data structures are updated, and then the enhanced pooling layer will reevaluate which new edge should be collapsed, which is this edge in this case. The rationale behind this is that by incorporating the information from the collapsed edge, the deep edge features will be improved. The authors showed improved performance and strengthened the learned features. Like you can see here that the high feature norm activations that are shown in red, they effectively learn to activate over more semantic regions in the enhanced version. So the input features plus convolutions are invariant to rigid transformations in many of the works that I just discussed. Not all of them, but many of them. And this can be a really effective inductive bias, especially if we know that our task at hand should be agnostic to arbitrary rotation, like for example, in shape classification and shape segmentation. But depending on the task, being invariant to rotations might be too restrictive. For example, in 3D printing, a key challenge is to find the rotation that you'd like to print. There are multiple viable orientations that can be printed, but some rotations are going to cause failure cases. And so different rotations have an effect on the amount and the type of the support structure needed, as well as other structural properties. And this brings me to a larger point that I want to make. There's an interesting trade-off between expressiveness and generalization. If we force the network to have invariances, we can better guarantee generalization, but this may come at the cost of the expressiveness of the network. And how to balance these things will again be specific to our task at hand. One way to break the shift invariance of the convolutional filter is to modify the input features with a positional encoding. In its most basic form, it gives some global position information about where the narrow MLP is in the image. And this concept is really starting to take off now in images. We see that it gives more expressive power and helps the network better fit to the data, especially for synthesis tasks. We can consider the same, like a similar simple injection of positional encoding in our convolutional filters, which would similarly give more global information, and depending on the task, could be a desirable thing. While we saw that for tasks like shape classification and shape segmentation, rotation invariance is desirable, but there are other tasks that may benefit from the shape orientation, not just 3D printing, but possibly also synthesis. The networks we discussed so far are extrinsic, so they're inherently sensitive to the mesh triangulation. And we can think of the sensitivity to these triangulations as a trade-off for more expressivity in our networks. In order to help our networks still be expressive yet robust to different valid triangulations, we can perform data augmentation. In practice, we've observed that training on data which has been augmented by a simple policy like using collapses, splits, and flips will enable generalization and robustness, and will still leverage and benefit from the advantages of the extrinsic mesh representation. In Mesh CNN, we show that we can still accurately compute semantic segmentations by simply training on edge flips of the data. And this enabled us to generalize to connectivities that were fairly different from the ones that we trained on. In our recent upcoming SIGGRAPH work, we extended this policy to more thoroughly cover the space of possible connectivities. And here we trained on edge collapses, splits, and flips. And this was key to enabling generalization on unseen shapes. Tying back to the earlier discussion on intrinsic methods, an inductive bias that they contain is that they can be invariant to triangulations. And this will trade off network expressivity for better generalization. For example, DiffusionNet showed robustness to different triangulations, resolutions, and even representations. In this next section, I'm going to talk about some applications of deep learning on meshes that learn from a single shape example. This is quite different from the most popular use of deep neural networks, which involves training them on big data, which would require generating large external training data sets. But this is especially challenging for 3D because, as I mentioned before, it's hard to obtain large amounts of geometric data that's watertight and manifold. And I'd like to bypass having to collect and annotate and learn from these large and complicated 3D data sets, and instead learn to leverage the internal data from within a single 3D shape without needing to pre-train on any external data sets. There is a lot of internal data within only a single shape. Shapes can have repeating structures or elements, and they often have symmetries. More generally, it's possible to represent an entire shape through a small number of local patches. And that means that similar patches must repeat within a single shape. So there is a lot of useful patch data, which is unique to this particular shape, and we can leverage and learn from it. I'll discuss 3 different works that leverage this idea of learning from a single shape example using some type of mesh convolutional neural network. Let's start with our point-to-mesh work, where we used mesh CNN to reconstruct a surface mesh from 3D scans. Surface reconstruction is a difficult and ill-posed problem. In point-to-mesh, we use the internal data within the given input point cloud for training a deep neural network to perform surface reconstruction. Normally, we would need to model 3D scanner noise to generate supervised external data to train on. But there's many different types of 3D scanners, and they all have very different statistics, which are difficult to model. And training on one doesn't necessarily imply generalization on another. In point-to-mesh, we train on the internal data given in a single input during test time, where the inductive bias of deep neural networks with shared weights results in desirable solutions. And this is what we call the self-prior. The self-prior bypasses the need to simulate or generate large amounts of external training data from a particular distribution, and instead, we train on the internal data given in the single input during test time. The problem of surface reconstruction is as follows. Given a set of points sampled from the surface of an object, we aim to recover the underlying shape. But surface reconstruction is an intractable problem, and it's been studied extensively for 20 years. Let me show you what I mean with a simpler example of a few points. There are actually infinitely many curves or surfaces that pass through these points. And another way of saying this is the problem is ill-posed. In order to pick a favorable solution or reconstruction result, this requires designing some type of prior, which will capture the expected shape properties. But building a prior is challenging, especially when shapes get more complicated than this simple illustration. Conventional techniques define a generic smoothness prior for reconstruction. But as you can see here, this will reconstruct holes in a way that ignores the character of the global shape. In other words, a handcrafted smoothness prior is too generic to tailor itself to any one particular shape. On the other hand, our self-prior is tailored to each individual input using a mesh convolutional neural network that's trained on the single given input point cloud itself. And this is the self-prior. It's going to produce a more plausible reconstruction because it learns the character of the shape. And we can see here that it's effective in completing missing parts and also removing outliers or noise. And since the mesh CNN has shared weights over the entire shape, it provides a good inductive bias that helps us avoid fitting to noise and outliers in the input. And so the reconstruction is actually going to be better than the input itself. Our self-prior works by shrink wrapping. We start with an input point cloud and some initial mesh, and then we iteratively optimize CNN weights to deform the mesh to shrink wrap the input point cloud. This strategy is actually really appealing because it gives us all sorts of geometric guarantees, like ensuring our reconstruction is watertight and manifold, and it can even preserve the genus. Because of these desirable properties, shrink wrapping has been attempted many times before, but these attempts were all considered unsuccessful. They required manual tuning or intervention to work on different shapes. But point-to-mesh successfully performs this shrink wrapping by leveraging the power of neural networks to learn from internal data. The optimized CNN weights act as a self-prior, and they encode the expected shape properties. The key to the self-prior is the unique structure of a CNN. On the one hand, convolutions are applied locally, and on the other, the same local filters are utilized over the whole shape. The premise is that shapes are not random. They contain strong self-correlations across multiple scales. Point-to-mesh works as follows. We start with some input point cloud, and then we use this to calculate an initial mesh. If we know the genus is 0, so we can compute the initial mesh using the convex hull. For non-zero genus shapes, we can use other techniques, and I'll touch on that a little bit later. The initial mesh is used as input to a mesh convolutional neural network, which displaces the mesh vertices, resulting in a deformed mesh. The deformed mesh is then sampled to obtain a set of points, and then we calculate the distance between these two, which is used to update the mesh CNN weights. We iteratively perform this update where the deformed mesh in the next iteration should more closely approximate the input point cloud. I really like this example because it illustrates how the network acts as a prior. If we directly optimize the mesh vertex locations instead of the CNN, it becomes trapped in this local minima. But if we optimize the CNN weights to displace the mesh vertices, then the mesh enters this difficult second order cavity. Here we can see exactly how the network behaves like a prior because it gives us a different result from the trivial mesh optimization. The self prior helps avoid bad local minima, which is key to the success of point to mesh. Previous works that try this type of shrink wrapping couldn't design this powerful enough prior and inductive bias of neural networks to avoid these local minima. So I think it really demonstrates the power of the inductive bias of mesh convolutional neural networks. We also used point to mesh to reconstruct objects that were scanned using a real 3D scanner. And even though there's noise and low density patches where the scanner fails to properly sample the surface, our reconstructions still handle these regions well. And those geometric guarantees I mentioned before, they come in handy because they'll enable us to even 3D print this. Here you can see that the self prior naturally removes noise from the corrupted input. And that works better than not only traditional smoothness prior, but also a network trained on external data. And other existing techniques don't utilize any genus information, so they can introduce topological errors and reconstruct a surface with the incorrect genus. Also, without any global weight sharing over a single watertight surface, it might be difficult to properly fill holes. Since the genus is provided implicitly to our method through some initial mesh, this provides control and it can be seen as an advantage for hole filling. In this example, Poisson reconstructs a surface with incorrect topological holes. So we applied a low resolution octree to close these incorrect holes, and then that created a coarse mesh, which we used as an initial mesh input to our technique. The result is a topologically correct mesh, which preserves the details from the input point cloud and doesn't overfit to these incorrect low density regions. So using a coarse resolution octree on the results of Poisson reconstruction is one approach for estimating initial meshes with unknown genus. Point to mesh can also handle unoriented point normals, which is a challenging problem in and of itself. We estimate unoriented normals in the input point cloud where each point is colored using a heat map of the angle errors. Existing techniques are sensitive to this incorrect normal orientation in the input, and that's going to produce undesirable artifacts. But a really nice aspect of our approach is that it's agnostic to the normal orientation. And since that's a prerequisite for surface reconstruction, we kind of bypass this need to solve this challenging problem altogether. In the next work, we'll see how to add resolution to geometries using a neural network trained on only a single example. Classic loop subdivision upsamples and adds more resolution to a mesh in two ways. The first is by dividing each triangle into 4 smaller ones. And the second is by moving the vertices according to some rules, like the weighted average. In neural subdivision, the network is trained to learn the policy for moving the vertices of the geometry instead of some handcrafted policy. The idea is to generate many different simplified versions of the same high resolution mesh, and then train a network to move the vertices back to the original location from which they came. But the high resolution mesh doesn't contain the proper subdivision loop connectivity. We would like to train a network to upsample the coarse mesh and then move the vertices to minimize the distance between the network output and the ground truth. But the ground truth vertices no longer correspond to the loop subdivision connectivity, and there is no external training data set for this task. This paper proposes a way to compute the bijective correspondences between the output and the original high resolution mesh. So given a vertex on the coarse mesh, after subdividing it, bijective mapping is computed to obtain the corresponding point on the high resolution mesh. And then we train some type of mesh convolutional neural network on half edges to displace the vertices to the desired location. If a network is trained on many coarse versions of this shape during inference, we can apply neural subdivision on a completely different coarse shape and it still works. And here is the result of loop subdivision for comparison. The authors also showed that the network can even learn to do stylized subdivision. For example, given this input chair and networks trained on these 3 different shapes, the corresponding subdivisions will look different and geometrically stylized. So this geometric style also relates to our deep geometric texture work, where we learn to synthesize repeating geometric patterns from a single example. And the motivation to do this comes from the fact that creating 3D models can require incorporating repeating geometric structures or textures because they're characteristic of many natural and man-made shapes. But if we have to do this manually, it's very tedious. Ideally, we'd like to build a generative model to automatically add the geometric textures for us. The idea would be, given some brand new unseen object, we pass it to this generative network and it's going to add the geometric textures. Conventionally, training such a generative network requires an external data set. But in this case, it's quite difficult to obtain large data sets with the same geometric textures. And even if we had access to a collection of one type of geometric texture, for example, these quilted chairs, there are significant inconsistencies between examples, and this is going to make learning from this type of data ambiguous. But if we can learn from the geometric texture ingrained within a single exemplar, we can avoid needing to collect and annotate large data sets and prevent these inconsistencies between examples. The internal data within a single shape represents exactly the geometric texture that we'd like to automatically learn to synthesize. And we can learn from the patch data from within the single shape, since textures self-repeat at the patch level. What's incredible is that even though we only train a single example, our network can still successfully synthesize the exemplar's geometric texture over a new unseen object that never contained this texture before. And this is possible because local patches look similar even for very different shapes. Our training procedure works as follows. First, we automatically remove the geometric textures from the exemplar by coarsening the mesh. And then we extract local untextured patches and train a mesh CNN on the triangle faces to displace the vertices back to the original location from the exemplar. And we train on a lot of local patches from this one exemplar. When training is complete, given a local patch from a new object, our generative network will still work, even though the new object is globally very different from the training example. At the local patch level, it is very similar. And I think this local patch-based idea is powerful because it's really what enables us to generalize on new shapes that we never trained on. We don't just learn to synthesize in one shot. We incrementally add progressive textures using a series of multiple generators that learn from each texture scale. We extract these intermediate texture scales through an automatic procedure that we created to incrementally rebuild this texture. And you can think of this like creating more training data, again, from this single example. Our approach works in 3 phases. In the first phase, we create the multi-scale texture training data from the 3D exemplar offline. In the second phase, we use the multi-scaled inputs as supervision to train a series of progressive generative networks. And once we finish training, we apply the series of multi-scaled generative networks to unseen shapes to synthesize geometric textures. The gist of our approach is we train a series of generators which progressively add geometric detail to the evolving mesh. We learn the unknown texture statistics from local triangular patches. Starting with this untextured mesh, we learn deep features on the faces of the input triangulation, which are used to generate vertex displacements. This output is loop subdivided before going to the next level generator, which displaces the vertices. And this is repeated until reaching the finest level in the series. Here are some results of training on the following exemplar and the multi-scaled textures that we extracted. Our network progressively adds this texture to a new unseen shape. Starting with the coarsest level, the unseen shape progressively evolves through each network scale. We can also interpolate between different variations of these synthesized textures, and this results in this neat animation. So in this talk, we looked at interesting ways to build convolutional neural networks directly over the mesh elements in spite of their inherent irregularity. We also saw that it is possible to leverage the inductive bias of mesh convolutional neural networks to learn from single shapes without needing any external training data. Despite this encouraging progress, I think we're really just getting started to understand how neural networks can be used to further our capabilities in geometry processing. I think there's a lot of interesting open research questions to investigate, but I just want to highlight a few avenues that I'm personally pretty excited about. I think it will be exciting to train neural networks to learn to correct, edit, and manipulate mesh connectivity. Like, can we generate a mesh with sharp features? Can we learn how to fix non-manifold geometries, close boundaries, and other things? And of course, can we learn to do this from a small amount of data or even no external training data? And another thing that is interesting to think about is having neural networks learn to automatically extract pattern, structure, and relationships in shapes. And analyzing these patterns could enable us to generate more variations of a small amount of shapes. And another way of saying this is, can we generate more of the same? And in order to achieve some higher level editing tool, I think it would be interesting to think about how to incorporate and mix elements of one object with another, such that one shape can take on the style or functionality of another, even across completely distinct shape categories. And these are just a few exciting directions, but I think we will be seeing a lot more applications in geometry processing in the near future. So thank you for listening, and I'll take any questions.
Thank you very much, Rana, for the very nice talk. I really like the idea of learning from very small data sets. That's quite good. So it's now time for the Q&A. Remember that to ask question, you need to raise your hand on Zoom, and I will call you. Before we start with Zoom, we got a question on Discord. And so cool, the shrink wrapping method could be used in point2mesh, could be used for shape approximation, like to generate shape proxy, for instance, like we've seen this morning during Tammy's talk.
Yeah, so I didn't see the talk, so I don't know. Maybe you can just like
Okay,
summarize.
so yeah, the idea would be to have an approximation of the shape that could be used to drive simulation algorithm.
To drive a simulation, you said?
You got a bonding mesh approximating the shape. So it's not only a decimation, it's also decimation and bonding the geometry.
Yeah. So I'm not sure if I don't know, like the voice isn't too clear, but if I understood you correctly, it's like a physical simulation of the like approximating the surface of something that's like not intersecting or something like that.
Yeah,
And if, yeah, okay. So if, yeah, so right now the way that we do this does not guarantee that there is no self-intersections, and they do happen in practice. The way that we kind of, but you can imagine you could, because we start with something that's not intersecting, we could do something which would just like calculate each iteration and ensure that we're not going to intersect, because we know in the previous iteration we aren't intersecting. That would make it like more computationally expensive, I guess. And we didn't really look into it, but I think it's definitely something interesting that could be looked into. What we did in practice was we used, we did this in a course-defined way. So every time we upsampled the mesh, we did kind of process it and ensure that it wasn't intersecting in the next like level. So.
Okay. Thanks. So we get a question from Marcus Forschel.
Hey, great talk, very inspiring work. I was wondering, what is like the typical mesh size you were processing with your network? Like, does it scale to very large meshes, like 100K faces, 100 million faces? And if it does not, what does it take? Maybe what could be future avenues to make it scale? Because certainly on large images, or we are seeing works which are more and more processing large images, and what do we need to process large meshes with these methods?
Yeah, it's a good question. So when we implemented this, I guess like we didn't really have in mind when we implemented mesh CNN, we didn't have in mind that we were going to use it for other things. Like, right, sometimes research can be very